pausing this. You guys know what the Math 15s are. You're simultaneously enrolled in a Math 15A, although we never did that. That was so that they could give us extra time. That's why the simultaneous enrollment you guys had with 119 and 15A, you never did the Math 15. They did that so that we would have more than 3 hours a week. That's it. Okay. It's a paperwork thing. Literally, it's a legalistic paperwork thing. Otherwise, a 3-unit class can only have 3 hours of lecture, but we have many more hours available. That's what the 119X is. So they do the X with the trig, they do it with the pre-calc, they do it with all these courses. It allows them extra time. But if you're going to take a math course next year, doesn't matter what it is, you're gonna take an algebra course, you can take anything next year, I would highly recommend doing a 15. The 15s are the review/refresher courses. It's the online self-paced. I've been managing them for many, many years. And I have my calculus students too. So I have a calculus student who, they understand calculus, but their trig skills are really weak, or some of their algebra skills are rusty. Maybe it's been a long time since they've had a math class, and now suddenly they're sitting in a calculus class, but their prerequisite skills are, I highly recommend these students will take the 15s to shore up their basic skills, because there's so many levels. It goes from pre-algebra through pre-calculus, but I'll have them take the 15s on their own, get up to where they need to be, and then they can be done with it and move on. The 15s, I am an absolute fan. Think of it almost like an online tutor, yet it's like, right now it's $30 or $25. It's 6 weeks of unlimited access, but we're starting to switch over the way me and the chair, Professor Ballou, are kind of redoing some of the 15s because we're trying to make it free.
And you run them?
Yeah, I manage them. But what we're doing is starting this summer, we're offering 15s that actually have support. So normally you would go home, you said, I'm gonna work for 2 hours on my elementary algebra review. Because it's something like this. You have to take an algebra class and pass it before you can move on to the next class, let's say. But you're going, I had that in high school. I'm a little rough around the edges. I forgot a lot of stuff, but I really don't want to retake an entire class that I've already succeeded at once. That's why 15s exist. So you take the 15 not to replace the course. No. You don't take it for a higher course. You take it for a course you've already done, but you need the review. You need the refresher. It's been too long. And a lot of people make the mistake of thinking they can take the 15 in place of it. No, it's a review/refresher. I've never had trigonometry, so let me do the 15 trigonometry so I can bypass trig. No, that's a disaster. You're not going to learn trig in doing online computer. You've had trig, but you need to review trig because you forgot a lot of it. That gets you back up to where you need to be, because you might have to take a challenge test. Okay, because you have to prove that you've done this, because maybe you had it in high school or somewhere else. The 15s are awesome. And there's going to be a lot of them this summer. And the summer is the perfect time to take them, because first day of the fall is not the time to find out, oh, shoot, I'm not ready for this class. I need to go back and do a refresher. Well, now you've just lost the whole fall semester. And by the way, does that happen? It happens a lot. People sign up for a course, realize they're not ready for it. Yeah. And so what you do is do the 15s over the summer. And I'm supposed to sell them to you guys. I don't really need to sell. They sell themselves, but a lot of folks don't know they exist. Yeah. They are online. And so what you do, the way it's always been is you log on at home, you work as long as you want. It gives you progress. When you miss a question, it will tell you what you did wrong, give you another similar question. It's one of those. You don't move on until you get that topic. And so it's interactive in that way, which is awesome. There's explanation. And the funny thing is, people say, well, I'll just hire a tutor. Well, you might spend 100 hours on the Alex. That's what the software's called, Alex, but you're only paying $25 or something. So in other words, you're getting it for pennies an hour. I don't think you want to hire a tutor. That would be really expensive. It'd be thousands of dollars perhaps. So it's a really good situation. So if you have to take more math, that's why you would want to do this. If this is your last math class, then there's no worries. But very few people can say that. That's the thing. And even the calc and above folk, I know, Salvador, you were talking about you want to go higher in math. Well, you don't want to retake, your algebra and your trig and your pre-calc. 3 years from now, you finally start calculus. You don't want to do that. You never finish. Yeah. And unfortunately, the way the system has always worked, it's always been like that. And I don't know if you guys are familiar with AB 705. That's sort of been the devil for a lot of people. It was a law that's passed a couple of years ago. They're basically, the state of California is trying to get you guys through faster, because what was happening is too many people were starting at the bottom and it was taking them forever. And so therefore they never got to the STEM courses, because, you know, after a few years, you just give up. So this said, no, we need to streamline this. We need to get people through faster. But that means people will be taking classes before they're ready. Yeah. So automatically the fail rate, guess what? Skyrockets. 3, 4, 5 years ago. Let's go back, say 5 years. The two most popular classes in the entire math department were Math 46, elementary algebra, and 96, intermediate algebra. Think of Algebra 1, Algebra 2 from high school. Those were the most popular courses. They're completely eliminated, by the way. They're gone now. We used to offer like 30 sections of each. They're gone because the state says, no, we got to get people out of that.
It takes too long.
But the flip side is the state of California is also saying now, this is an interesting thing. This is a recent thing I just found out. One of our retired high school teachers showed us an article that California had the lowest math standards in the US just about, by the way. You only needed to have Algebra 2 to graduate. Now, when I was in high school, you had to have at least 3 years, and Algebra 2. By the 90s, you only needed to have Algebra 1, and then they realized people weren't ready for college, so they upped it again. So Algebra 2, which most kids take around 11th grade. Okay, you need algebra, you have to have Algebra 2 to graduate. Well, the recently come out and said, why do you have to have Algebra 2? If you're not a college-bound kid, let's say you're going to go vocational, why would you need this class? And by the way, being a math person, I agree with this, saying, if you're not going to do anything STEM related, better to teach you skills that you can now use in life. That's sort of the argument. So California is now moving away from making Algebra 2 a required class. They're going to lower the math standard again. Okay, I never like lowering standards, but we're going to lower the standard. Well, why is that a big deal? We're going to lower the standard. So you're going to have kids, a huge number of kids graduate from high school, having only had remedial algebra. Now they want to go to college, and guess what? All of those other algebra courses are no longer taught. The next lowest class is pre-calculus. How do you go from remedial algebra to pre? You can't. It's not math. It's not possible. So what we're doing by changing the way we do things at the college level, by eliminating the lower level classes, but in high school, we're dropping the standard for graduation. We're creating a massive gap. Yeah. That students, when they want to go to college now, how did they fill that gap? Do you see the dilemma here? Imagine, I'll use like baseball as an example. Baseball, I'm not a baseball player or a baseball fan. Baseball has multiple layers of minor leagues, agreed? They have, I think it's called single A, double A, triple A. Triple A is right before they get to the pros. Single A would be you're a high school stud and you sign that contract and you want to do that. So a high school kid who's really good goes through these levels of the minor leagues. If they're really good, they go through them really fast. Maybe they only spend a couple of years. Other people might spend several years, but they go through these levels. Okay. If you're a football player, what's the equivalent of the minor leagues? College. You go through 4 years of college and then you consider going to the pros. Imagine we eliminated the minor leagues in baseball. We eliminated college for football and basketball. That means as a high school player, the next level would be professional. Yeah. Is anybody going to make it? No, there's not even a chance. There's just too much you have to do. There's too much growing up physically, mentally. No, if we eliminated that middle level, we'd basically kill the sports because people would not be able to develop anymore. Mm-hmm. Well, we're kind of doing that right now in mathematics. We're eliminating the middle level. And that's a scary thing. So the 15s that we have are going to become even more important. I think right now the feel is they may be the stopgap to kind of replace. The fact is when you're coming out of high school, and a lot of people, they come out of high school, they don't want to go to college yet. They're not ready. They go out, they work. Maybe they go in the military. Are you? Yeah, so that's what you did, right? You went in the military. And that was probably the smartest thing you could do because you probably grew up and say, okay, now I know what I want to do. But now high school is even further in the past. So you remember a heck of a lot less than when you're 18. And now you want to go to college. Well, where do you start in the math realm when you go to college? And that's always been the big issue. The hardest math class people generally have, it's not a specific class. It's the first class they have when they come back. It doesn't matter what it is. It's whatever the first class is because you forgot how to be a math student. I'm guessing, right? But you didn't graduate from high school in the last 2 years.
In
guessing.
1990.
You don't have to.
Oh, sorry.
I'm saying, in other words, you don't, it's not recent. Therefore, why would you remember? I had 3 years of high school Spanish. Barquito is boat, zapatos is shoes, and baño is bathroom. And I don't remember a whole lot else. You know, and I live in San Diego. There is, I don't speak Spanish. I don't practice my Spanish. Why would I remember any of it if I'm not? Well, is there any difference with math? No, math is a language. If you're not practicing the math, you forget the math. That's why it's so important that you guys set yourself up for success if you're going to go on and do more. You don't just jump in head first and say, I'll take my chances, because usually that doesn't end well. And that's unfortunate. Now, Danger is her middle name, right? Okay, so let's get to our stuff. So we're going to do 2 forms of hypothesis testing this week. Today we're going to do hypothesis testing on P. That way all the problems and examples we do today will all look the same. And then we're going to do on mu. Those are the 2 biggest ones. Now here's the big picture overall. There's a situation that occurs. Maybe it's you're watching a commercial on TV. Maybe it's advertising, or maybe it's just something that you've read recently, or you know, I just wanted to see if this coin is a fair coin. There's something where there's a probability assigned to something, and you're saying, I want to demonstrate whether that's true or not. I don't know if it's true or not. Now, I've given you several examples in the next quiz. We're going to work on that. But it could be something as simple as, I have a coin, I want to determine it's fair. I have a die, and I want to determine if it's fair. Well, how can I do it? We'll just roll it a whole bunch and see what the outcomes are and see if they're what they should be or if they're way off. This is one that I used to use. You guys are too young now to remember this. Back in the 90s, okay, San Diego hosted a Super Bowl in '87, I think it was. Redskins were playing the Broncos. It was the last time we hosted a Super Bowl. And the NFL basically said, the stadium is too terrible. We don't want to do a Super Bowl. You guys need a new stadium in San Diego. And people were like, oh, you know, and I'm a big sports fan, but I've always been absolutely opposed to public money paying for a billionaire stadium. And a lot of cities have been held hostage. In other words, tax dollars building the $1 billion stadium that the billionaire owner owns, or basically gets all the revenue and says, hey, I'm going to get the city to pay for it. I've always had a problem with that because they're not giving me free tickets. That's right. I'm going to pay for your stadium. What am I getting out of it? That's always been my attitude. Yet teams will say, well, then we will move if you won't build us a stadium. So there was a poll that went around. And at that time, the funny thing was, I knew the mayor, Mayor Golding. I knew her. I'd taught her daughter in high school for 3 years, and I knew her before she was mayor. We were actually loosely friends. If she'd see me, she'd wave and talk. And the city's district attorney, Casey Gwynn, I went to a tiny high school in Santa Cruz County. He was 1 year ahead of me at my high school. So the DA and the mayor, I knew. And they came out and said there had been a recent poll, and the number, I don't remember exactly, it was like 63 or 67% of San Diegans approve public funds going towards the stadium. So they put something like 60 or 70 million dollars into the stadium to fix things, not a new stadium, but to fix things. And there were a lot of people that were very upset. And for a lot of reasons. One is the public money going, but one of the biggest reasons, and I remember was reading saying, where did these numbers come from? They said a poll had been taken and was overwhelming that San Diegans supported this. And that's the thing I used in my stats class. I said, you know, it's interesting they came out with these numbers because multiple polls were taken after to ask San Diegans, and they came up with numbers that were significantly lower, meaning maybe they made it all up. And at the time, there was a deal made with the Chargers, and you guys, again, you're too young to remember, the city made a deal with the Chargers to buy up any unsold tickets every week, because a team can never be on local television. You ever heard of blackouts? They call them blackout rules. A team cannot be on local television in the NFL if they didn't sell out the game a certain amount of time beforehand. That was always an NFL rule. Now, the game could be telecast in other cities, but it would never be telecast local if it wasn't a sellout. So the city agreed to buy up all unused tickets every single week. that had never been done in professional sports in the United States before or since. And so the Chargers were the only professional team in any sport in the United States that did zero advertising. They didn't spend a penny on advertising. Why would they have to? The city is buying up all the tickets. And the Chargers were the least attended football team of it. They were the only team. I've been to many Charger Raider games and stuff. They're the only team in the NFL where, generally speaking, there are more fans of the opposing team at the games. So a Charger game would have 20,000 empty seats. Can you imagine an NFL game having empty seats? But every week. So the city bought up the tickets. And that was that mayor. And that was not legal, by the way. But they did it anyway, and they were stuck with this for several years. And they also convinced the city that all these repairs were necessary. So they spent all this money on repairs, and then the NFL still said, no, the stadium's still too crappy. But what they did was they claimed a percentage of San Diego. So in other words, it's the hypothesis test we're going to do today. They made a certain claim that said this many San Diegans believe this, and other people were saying, we don't believe that. But here's the problem. When someone makes a statement like this, this is a product. You know, I'm on TV and I'm advertising my product, and you're saying, I've had that product. There's no way. It's not that good. Is the burden of proof on the person who's telling you about the product, or is the burden of proof on you to say, no, it's not very good? Yes. Yeah, it's on you. You can't, it's like somebody proving their own innocence. No, you don't have to prove your innocence. You have to prove somebody's guilt. You assume the innocence, and then you have to say the evidence shows you guilty. This person who's advertising on TV has every legal right. Now, there's stuff called false advertising. They can get in trouble if it's proved that they're lying. But they don't have to prove they're telling the truth. We have to prove. Does that make sense? Yes. So when they're saying our product does all of this stuff and is this good, so you start with saying, okay, I will assume your product is this good, but if your product's this good, then our results better be really good. Because if our results are really terrible, then we can say, no, you're not telling the truth. You've got to change your claims. And that kind of stuff does happen in real life. And it all comes down to what we're talking about, hypothesis testing. So in a hypothesis test about P, okay, we're going to do a test about the probability of whatever it is we're measuring. And still we call it probability, except it's whatever we're measuring. So if we're talking about the poll of San Diegans who approved the stadium renovations, P would be that you said yes. Q would be you said no. Okay, so if 0.6 is 63% or 0.63 said yes, that would mean my P is 0.63. Does that make sense? Oh, then my Q would be whatever's left over. Okay, so we're doing a test about P. So I have a null and I have an alternative hypothesis. And we talked about this last day. The null hypothesis has to be the equal. So the null, there's three things null can be. That P is equal to some number, and then the alternative would be that P is not equal. I'm just going to put generically some number, whatever the number is you're measuring. This is 1, okay? A second one would be that P is greater than or equal to some value. If it's not greater than or equal, then it has to be what? Less than, because that's all that's left. Remember, you got to cover all bases. Or the third possibility is that P is less than or equal to some number, in which case the alternative would be P is greater than. When you're doing a test on P, it's one of these three things. How do you know which one it is? The language used. So the city officials are saying, we did a poll and 63% of San Diegans felt this way. Now, when remember, they're doing a poll. They didn't ask every single person. But if they're saying 63%, are they saying exactly 63, less than 63, at least 63? In other words, if more than 63%, nobody's going to say you're lying. They're only going to say you're lying if it's way less. So when they say 63%, what are they really saying? At least. Does that make sense? They're saying at least 63%. Because we talked about this last day. Most things in real life are actually inequalities. We just don't always say at least or at most. You can miss 6 questions on the driving test. But you could also miss less than 6 questions. Missing less would be good too. You just can't miss more than 6 questions. No more than 6. 90% will get you an A in this course. Yeah, but so will more than 90%. Right? Does that make sense? When we use, a lot of times when we speak, we're really using an inequality. There's an at least or an at most in there. So if the city is claiming that 63% felt this way, they're saying at least 63%, not at most, or not exactly, because remember, it's a poll. It's not every single person. So what has to happen is you're going to go out and do your own separate poll, and you're going to try to show that, no, this is the truth. So here's the way all hypothesis testing works. Whatever the null hypothesis is the truth, or at least what you're assuming is the truth, and you're going to let the evidence tell you otherwise. You're going to assume the person is not guilty, and you're going to let the evidence convince you in the other direction. Does that make sense? And by the way, can it be weak evidence, or does it have to be overwhelming to go the other way? It has to be overwhelming. And when you're talking football and you want to overturn a call, well, that's pretty close. Let's go ahead and overturn the call. No, it has to be overwhelming, right? Irrefutable, they often say. No reasonable doubt. You can't say, well, they claim this and, our evidence is really close. Let's go ahead and go. No, it's got to be overwhelming. That's just how it works in reality, because you don't want any decision to be questioned saying, well, what were you basing it on? That would be like in a court of law. We found the person guilty because, we didn't like the way they dressed. The evidence was kind of weak, but no, you don't find them guilty unless the evidence is overwhelming. You're saying, I'm going to assume innocence, and the evidence has to be overwhelming to convince me of guilt. I'm going to assume whatever the null hypothesis is, and the evidence in front of me, the numbers that I collected, my sample, has to be overwhelming for me to go the other way. It's actually that simple, because we talked about earlier, we want it to be black and white. We don't want it to be gray. We don't want to say, well, gosh, it could go either way. No, it can't go either way. So what we were going to do in each case is create a line in the sand. If Z is bigger than this, if Z is smaller than this, whatever, we're going to create a line in the sand that's an absolute number, and we have to fall on one side or the other of that number. And then we can make our decisions. So in a hypothesis test, this doesn't take any mathematical skill. I'm just taking the situation and I'm writing it down. But if I don't get this right, I'm going to make the opposite conclusion. Okay, so that's step one. Step two is now what we call the criteria for rejecting the null hypothesis. Because the only calculation you're going to do is you're going to calculate a Z value. You're going to do a Z calculation, and I'll go over it because we have all the formulas in front of us, and there's only one formula we're going to use today. We have to calculate a Z, and that Z is on one side or the other of my line in the sand. So the criteria for rejecting the null is we're going to choose what Z value will cause rejection. Now, remember I just said there's three different cases here. The first case, I'm going to give you a simple example. The first case is I'm trying to test whether a coin is exactly 0.5 or not 0.5. Getting heads or tails. Not whether it's at least 0.5. A fair coin is a fair coin if it lands heads half the time and tails half the time. Do you agree? We don't say it's fair if it lands tails at least half the time. So if it always lands tails, we'll call it fair. No, it's got to be exactly half the time. I call that die fair if it lands each number 1 through 6 exactly 1/6 of the time. Not, well, as long as I land the number 3 at least 1/6 of the time. No, I have a 6-sided die with the number 3 on every side. Right? It's always going to land 3s. We'd agree that's not a fair die. More like a Harvey Dent die. So in this case here, we're going to say, in each case, we're going to state, I'm going to call it the magic, no, I don't, no, I'm sorry. I'm sorry. Let me write this way. We're going to state, let's just call it the magic Z. We're going to look up the Z. We had the 005, the 01, the 05, right? We had the magic numbers. We're going to talk about that. We're going to state, this is our line in the sand. Now, I said, we're going to call the calculated Z. Oh, sorry, we can't write today. We're going to call the calculated, or the measured Z, calculated Z. We'll call it Z star. That was the term I used the other day, because I'm going to have a Z that I'm looking up and a Z that I'm calculating. They're not the same Z. One is this constant that I'm looking up, and the other one is the one who I plugged into my calculator. So I'm going to call Z star the one I'm plugging into my calculator. So in this case here, what will cause us to reject? We will reject. Now, always there's a picture. Okay. In this case here, I'll draw a different picture for each one. Equal versus not equal. I'm going to reject if it's extreme at either end. Do you agree? Either end. Because this is an equal versus a not equal. So I'm going to reject if I'm either way too big or way too small. But I'm not going to reject if it's anywhere in between. I'm only going to reject in either extreme. This is called the two-tailed test, remember? Because it's equal versus not equal. Not equal would be either too big or too small. So in this case here, we will reject if my measured Z is bigger than Z, alpha over 2. Remember, alpha is the 5% or the 1%. It's one or the other. There's only two we use. Or if the measured Z is more negative than the negative of that guy. Remember, what is this? That's that. What is this? That's that. I'm going to reject in either extreme. So here's what happens. You state all of this before you start the problem. In fact, you state this before you even collect your data. Now, I collect my data. Maybe as I sit there and I flip a coin 1,000 times, that's my data. Now, where do my results fall? Do my results fall in here, or do my results fall in here? Do you agree? It's got to be one or the other. Either my results fall in the middle area, or it falls in the extremes, either extreme. If my result, that's the line in the sand, that's the black and white. If my results fall in the extremes, then I reject the null and say, nope, that's not the truth, that is. If my results fall somewhere in between, and we're going to get used to this because I'm going to do a whole bunch of examples, the language is fail to reject the null. Now, if I fail to reject the null, does that mean the null is the truth? And this is what's kind of weird. If I fail to reject the null, it means there was not enough evidence to reject the null. I think you're guilty as sin. We went to trial and 11 people voted guilty and one person voted not guilty. And so you're not guilty. You're not innocent. You're just not guilty. Why? There wasn't enough evidence to prove your guilt. Because there wasn't enough evidence to prove guilt, does that mean anyone believes they're innocent? No, it just means it wasn't enough. They were almost guilty. They were just right on the edge of being guilty. They just weren't quite guilty enough. And that's actually how it works most of the time. You either reject the null or you fail to reject the null. You don't say the null is the truth necessarily. You just say, I don't have enough evidence to reject the null. If my evidence fell right here, you'd say, yeah, the null is the truth. But what if my evidence fell right on the edge or right on the edge? You're saying, there's not enough there. I almost. But that, it doesn't mean you believe the null is true. It just there wasn't enough evidence. And again, I want you to always equate this to like a court of law because it's actually the same language and the same logic and the same mathematics, believe it or not. We assume you're in here. We let the evidence determine if you're here or here. If you're here or here, you're guilty. Guilty would be I reject the null. I reject the not guilty assumption. Does that help think of it that way? Now, that's the first case. The second and third cases are very similar. These are called one-tailed tests. I'm only going to reject in one direction. So the city comes out and says, you know what, 63% of people felt this way. Roz like, I do not believe that. None of my friends and neighbors feel that way. So you conduct a fair, unbiased poll. You ask 1,000 people. And you ask 1,000 people and 67% of them said that they approve. And you're going to go, oh, the city only said 63 and I came up with 67%. Are you going to make noise? No, you're going to quietly go away and said they were telling the truth. You went out and collected it and you found only 37% felt that way. You're saying, liar, liar. You're going to make news. You're going to go on television. And by the way, that's what people did do. There was a guy named Bruce Henderson who was vilified, repeatedly vilified on the news and in the press, and he was the only one that was right. It took years before he sued the city, and it took years. This guy was saying, they're screwing us, they're lying to us, they're stealing from us, and everyone, oh, no, you're just a hater. He was right. Because what they did was they did shady backdoor, they call them what? backdoor dealings and backroom dealings. They did stuff. The mayor and the city attorney should not be doing things financial to help a billionaire owner out, regardless of where you feel about anything. That's not something that they should be doing. You know, when they built the ballpark, what's it called? Petco. I remember when that was before the city ordinances, and I would go into the gym all the time, and I would talk to them. Oh, everybody was for it. I said, why are you for it? They're going to tax you and make you build. Oh, because it's going to do so much for the city of San Diego. I said, who's it going to do? Oh, well, all this revenue brought in. Turned out the only people that benefited were the hotels and the restaurants that were within like a square mile. And those were the people that were spending all the money to support this. And they did really, really well. And by the way, parking structures came up that made money hand over fist, because my in-laws have seasons tickets every year, and they pay an ungodly amount of money every year so that they can park a car, because there's no parking apparently at the stadium. Restaurants, hotels, and parking structures within like a mile of the stadium are the only San Diegans that benefited. But we were told that everybody in San Diego is going to benefit. Nope. The only businesses that benefited were those that were right there by the stadium. I mean, how are you benefiting where you are at home? I'm benefiting as a teacher by their existence. No, but I had to pay for it. I had to pay for that stadium. You know, a little bit of money, but I had to pay for it. I had to pay for the renovations on, you know, the Qualcomm. Back then, it wasn't called Qualcomm. Remember what it was called? The Murph. It's called Jack Murphy Stadium for a long time, and then eventually it was Qualcomm, because Jack Murphy was a San Diegan. That he was some legendary. I think he was a sports writer, and they named the stadium after him. Then later, sponsors. You get to name stadiums after sponsors now. That's a totally different thing. That they get lots of money. So in this case here, we'll use this example. The city says this many people felt this way. So we're going to accept that as the truth, but we're going to go out and do our own research. We're going to do our own poll. We're going to find out. We will only reject it now in that extreme. So now here's what we're doing. We're accepting this as the truth, and it's going to require an extreme to the left. Why to the left? Because my alternative is less than, but my evidence has to be overwhelming, not a little bit. So Roz goes out and conducts her poll, and 62% of the people in her polls said that they want the renovations. Well, you know what? 62% is pretty darn close to 63, and you only did a poll. I remember we usually have a cushion, a plus or minus. So is that 62% really right on to what they're saying? Yeah, it really is. But you'd say, you know, there's a line, you know, if it keeps getting lower and lower and lower, there's a point where I'm saying, no, I can't say it's what they're saying. Even a confidence interval. And you guys can see that coming. We're going to show the calculation. That's actually the easiest part of the problem. So we will only reject in the left tail. So our criteria for rejecting this one would be, we will reject, we're on the middle one now. We will reject if the measured z is less than a negative value, because it's got to be the left, of the entire. Oh, it's not a two-tail. I don't cut the alpha in half. So now this would be Z01 or Z05. I put the line in the sand out there. I'm going to calculate a Z, and that's what will cause rejection. I will only reject, and again, it's got to be overwhelming. Yeah.
That's what you said, reject if the measured Z is what?
Less than.
Okay.
But not just less than the negative, because we want this tail.
Okay.
Does everybody understand why it's the negative? Because I got to go that way. I don't want to get into the legalistic thing, but when you start challenging people, let's say somebody's making a claim on TV. You think of a commercial. You ever watch a commercial and you go, no way? Because every other, no way. There's no way. But you watch a commercial and you say, I want to be I think they call it in the news, the consumer advocate. Everybody likes consumer advocates because they're on your side. They're trying to dig up dirt on people who make false claims. You're the consumer advocate, and somebody you think is being shady. And so you call them on it and you make an announcement, blah, 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 but you didn't really prove it. You're looking at getting sued, libel and slander, and you're going to lose. It's going to not end well for you. You can't just come out and say somebody is lying publicly. You got to prove they're lying. Do you understand?
Yes.
It's not like the old West, you know, Junior and I are playing poker and I think Junior's dealing under the table. So I got out a gun and we go at it because I think you're cheating me. You know, that was the old West justice, right? That doesn't really work. You have to prove it. You can't just say it. Now, what if you did prove it? Well, then, you know, they're in trouble. Okay. Third case. Now, third case is going to look just like the second one, but now we're looking. Now we know is something's at most this. This might be customer satisfaction. You know, at most 5% or 10% of the people send their meals back. You're at a restaurant. Maybe that's what you're measuring. Okay. You're only going to reject the null hypothesis if it's in the extreme in the other direction. So now rejection will be only at this end. It's a one-tailed test. Sorry, let me get rid of that part. It's a one-tailed test. Again, I start by saying I'm going to assume this is the truth. And now my evidence has to be overwhelming in this direction. That's what I'm saying. It's very similar to the previous one, but now we want to be overwhelming in this direction. Okay, so going back to this. Now what would this be? I will only reject if I am greater than the magic number. So by saying statements like this, you're requiring extremes. Now, can you ever be absolutely certain? No, but that's what the 95% or 99% level of confidence means. It means if you did the same thing over and over and over and over again. Let's keep it really simple. We have an alpha of 0.01, which that means 99% confidence. An alpha of 0.05 means 95% confidence. The simplest way I like to think about this, if I have the 99% confidence, if I do 100 different samples, or I have 100 people working for me and they each do their own independent sample, we're going to get it right 99 of the 100 times. That's what that literally means, that 99 out of 100 times, we are absolutely going to get the right conclusion. Is it still possible you did everything right and got the wrong conclusion just because the sample itself? So when Roz goes out and polls people randomly, independently, and does everything unbiased, and your sample numbers, could they still be wrong? Is it possible? Yes, not very likely, but it's still possible because you didn't ask everyone. Because it's a sample, there's always a small possibility that you got it wrong. But we're saying with 99% confidence or 95% confidence that 99% of the time you're going to get it right. And we can live with that. Okay. Does that make sense? We can live with that. So we're going to do a couple of examples from beginning to end. And I'm going to show you how to do the calculation and how to express your conclusion. And there's a few more little things. The work involved in a hypothesis test is not a lot. And it's a very standard setup. So let's do the city one, all right? Just to say the city of San Diego claims 63%, and I'm going to put in parentheses, that would be at least, of voters approve money spent on stadium repairs. This is actually what was going down. This was in the, I don't even remember what year it was now. This was back in the 90s. It was a long time ago. All right, the city of San Diego claims 63%. Okay, that's it. You believe the true probability is much what? More or less? Much less. Okay. You set up the entire hypothesis test and the criteria for rejection generally before you go out and collect a single piece of data. Okay. A lot of people make the mistake. Let's suppose that I'm trying to find a cure for cancer. I'm doing something. I set up my hypothesis. The hypothesis, my speculation, what I think is going to happen. Now I go out and do all my experiments and I see if my hypothesis is correct or not correct. Nobody on planet Earth, scientists goes out, I'm going to do a whole bunch of experiments, collect a whole bunch of data, then I'll form a hypothesis. No, you have the hypothesis first. That's the whole reason you went out and did your experiments and collected your data to see if they support your hypothesis or don't. Does that make sense? You know, I'm just going to go out randomly do things and then I'll form a hypothesis after the fact. No, hypothesis is the first thing, not the last thing. Right? The data has to support the hypothesis. Not the hypothesis is built around the data. It just doesn't work that way.
So the hypothesis in that would be you believe the true probabilities might test. That's your hypothesis.
So
No?
this is a greater than or equal. This is a less than.
Okay.
So what is my null hypothesis? That P is greater than or equal to 0.63.
Okay.
Because remember, the null is whatever includes the equals. It's not what they're claiming. Some people make the mistake of saying the null is what they're claiming. No, the null is either greater than or equal, or less than or equal, or an equal, whichever includes the equal, because an equal is something that I can measure. So what's my alternative? And it's less. Okay. You all agree with that? Okay, that's our starting point. Now, let's say you want to test this. You test at the alpha equals 0.05, and the words we use is level of significance. That means if I draw the picture, I'm going to reject for the bottom 5%. That's what that means. That's the tail probability. So when I do my collection of data and I do my calculation, I will reject the null if I fall into the bottom 5%, but everything else will not cause me to reject the null. You with me on that? Okay, so now you go out and you collect the data. Oh, we need to state the criteria for rejecting it, okay? So what is Z with a 5% tail? This is one of my magic numbers. There's only 4 possible magic numbers. This is one of them. What is the Z that corresponds with a 5% tail?
1.645.
Perfect. That is my line in the sand. Now look at my picture. Oh, okay. So I need it to be the negative, don't I? Because it's at that end. If it was at the right end, it'd be the positive. This is a number I looked up. This is not a number I calculated. When we do our calculation, I'm comparing it to what? This. So I will reject the null hypothesis if my measured value of Z is less than what? The negative, because I'm on the left end. If I say, what's the problem if I don't put the negative here? You remember one tell me? Then I would be rejecting everything. Check this out. That's 1.645 at this end. That's the highest 5%. If I put less than positive 1.645, that means I'm going to reject almost all outcomes. Even I'm going to reject pure truth. Do you see a problem with that? I'm going to reject everything. No. I'm only rejecting here, not here. So that's why it's important that now I've stated my null and alternative hypothesis correctly. I've stated my criteria for rejection. These are critical because these are the only things you have control over. Now you're going to go out and collect data. You don't have any control over what people are going to say. You just collect it. You don't have an opinion. You say, I'm going to ask a lot of people. And maybe you set it up so you've employed everybody in the class. You have them all over town, all over the county, asking as many people, and we collect a whole bunch of data. That's a good way to do things because you want to nail the city. You don't want to ask 5 people. You maybe want to ask 5,000 people. So now we've gone out, we've done the data collection. So here's what we found. I need to write it somewhere.
How did you get 0.05?
Because I said that's what we're testing at. You're going to test it at that. That's done ahead of. There's only 2 levels you're ever going to do, 05 and 01. Now, what's the difference? Well, it's easier to reject an 05 than it is an 01 because an 01 is even more extreme. But it comes down to things like this. If it's a life and death thing, if I'm talking about a medical situation, blah, 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 blah. 01, if it's life and death medical, is usually more common because I don't want to even take a chance that I made a mistake. Most things are going to be an 05 level. And those are the only two we ever really use in real life.
So in a problem that will always be stated.
Always stated.
Okay.
There's no ambiguity there.
Okay.
So it's saying, okay, Roz, you want to test this at the 0.5 level of significance, which means that you want your tail probability to be 0.05, and that's what you're going to call the extreme. I'm going to reject it in the lowest 5%. If it had been the 0.1, you'd reject it in the lowest 1%. But that's always ahead of time. And again, the situation in real life, I'm the FDA and there's a controversial new drug treatment that may or may not work and a lot of things. I'm probably going to be at the 0.1 level because I want to make darn sure this thing is so good before I approve it because again, pharmaceuticals are the ones that have the hardest time passing. And that's a good reason. So if a pharmaceutical is out there on the market, it's been tested and it wasn't easy to get approved. And by the way, that makes you feel better knowing it wasn't easy to be approved. If things were easy to be approved, then there'd be a lot of bad stuff out there that would be legal and bad. We want to minimize bad stuff. So there are agencies that actually are out there just to protect us, like FDA, for example. So we go out and we collect our data. And here's what happened. You went out and you asked, let's keep it simple. You asked 500 people. Now, if we'll call X the number of yeses and you asked 500 people and you found that of the 500 people, 275 said, yes, we approve the stadium stuff. It doesn't matter how many said no, that's how many said yes. Okay. Therefore, what is my p hat? Remember, p hat is the measured probability. Think of this like free throws. 275 over 500. Agreed? So p hat is 275 over 500. And that's a nice number. That comes out to be exactly 0.55. And here's the thing. So Roz goes out, does everything right, collects the data, and she found that 55% of her sample said, yes, we approve this. I don't know what the answer is going to be, but 55, is that close enough to 63% or is it too far? I don't know. We're going to have to calculate it. But you would be a little bit suspicious. You go, there's a good gap there. There's a good gap. So now I'm going to show you the calculation. And by the way, does everybody have the formulas? Again, you need to have these formulas at some point. Let's see, is this on the net? Hold on. Now, here we go. Yes, it is on. Okay, it's on the third page, at the top of the third page. At the top of the third page is the formula. Okay, where it says test statistic. So write it down here. It says the test statistic Z, and I'm going to call it Z star because this is the one we're calculating. It's p hat minus p over the square root of PQ over N. Now, here's what is what? I got a P and I got a P hat, I got a Q. What's what? Here's this, I'm going to make this as simple as I can. If we're assuming that this is the truth, we're assuming then the city is telling us the truth. We're trying to prove otherwise. So we're going to assume that the actual P is 0.63. Our P hat is 0.55, but we're going to assume the actual P is 0.63. So when I put my numbers into this, I'm going to use 0.63 for this P. Therefore, what will I use for Q? 1 minus that, which would be 0.37. What am I going to use for N? 500. And what am I going to use for P hat? The 0.55. All of the numbers.
Can you repeat that?
Yeah, all of the numbers are right here. All the numbers are right in front of us. So we're going to, again, if the null hypothesis we're assuming is the truth, then we're going to say, okay, we will use 0.63 as the truth. So we're going to use a P of 0.63. We're going to assume that's the truth. So then Q would be 1 minus that, so 0.37. N is clearly 500, that's given. And what's our P hat? And by the way, you can leave P hat as a quotient if you want. If that's a terminating decimal. But what if that wasn't the terminating decimal? Then just enter the fraction into your calculator. That's always safe. Agreed? So what's P hat? I'll write it 275 over 500. I'm going to insert these numbers into here, and that's my calculation for the Z. Again, if we're assuming they're telling the truth, then we're trying to say, how if they're telling the truth, then our sample really shouldn't be very far.
Mhm.
And we're about to calculate that and see just how far away is our sample. So on your calculators now.
You're not giving us magic Z or
No, we looked up the magic Z. This is our calculated Z.
Oh.
Yeah, this is the only calculation. And we're going to compare this to the magic Z to see which side of the line is it on. Do I cross the line? When I literally mean you're drawing a line in the sand, and are we going to cross that line?
For Q, how'd you get 0.37?
How did I get what?
0.37 for Q.
If P is 0.63, what's Q? What is Q? What is Q always, no matter what? If P is the probability of success, Q is the probability of failure, which is what's left. P and Q have to add up to, yeah, this is not new. There's only like week 9. P and Q have to add up to 1. That's not rocket science, but if I don't have a Q that adds up to 1, then I'm going to be using all crazy numbers. We love it when P and Q are both 0.5, don't we? But that's not always the case. So what's Z star? It is. And I'm going to write it as 275 over 500 just to remind me, oh yeah, it is 0.55, but it's not always going to be a happy decimal. So I'm going to write the actual P hat minus we call it the hypothesized P over the square root of the hypothesized P, the hypothesized Q, and the actual N, which was 500. Okay.
Yeah, right.
Now, you're going to need some parentheses here. Let's walk through this. Now, you do parentheses on your numerator. So let's all do this. So parentheses on my numerator, and then close your parentheses.
Wait.
For parentheses around your numerator, you can't ever get a correct calculation without parentheses. You've got like
On the numerator at the bottom.
Yeah.
Sorry.
numerator. Got a parentheses on the numerator. Now, the nice thing is you only need one set of parentheses on the bottom. The parentheses I put around the numbers are for readability only. I don't need parentheses around numbers when I enter them into my calculator, do it. We do that so we can see, oh, okay, I don't want the numbers running into each other. It's easier for me to read. Now, you've got your parentheses on your numerator. Now hit divided by square root. Now, I want all of this in my square root. So now I put open parenthesis. Now, do this times this divided by this, close your parentheses. That's it. So this times this divided by this, and then close your parentheses. So
I want a negative.
points, you should.
Okay. I'm at negative 3.7. Are we rounding to like?
Well, that's a Z value. Yeah, so 2 places is probably good.
Negative 3.71.
Okay, now why am I getting a negative? Because my P hat is smaller than P. So my numerator is negative. Do you agree? Your measured P, the P hat was only 0.55. Your assumed P was 0.63. So tell me if you guys got the number.
Yes, something.
Negative 0.37 something. All right, so you got negative 3.7, approximately 3.71. All right, so let's look at our table here. So when I look up negative point, oh, wait a minute. On my table doesn't go past negative 3.5. And what does it say for negative 3.5 and lower? It says it's really, really unlikely. This is going to be an easy, by the way, an easy decision to make. Yeah, Roz, you get the right answer?
No.
Uh-oh.
But at least I can see my calculation.
Oh, you don't have
What did I
the,
do wrong?
you didn't do the divided by 500 on there. And there's no parentheses.
Oh,
The parenthesis is left open parenthesis here, then this times this divided by 500, then close. There's no parentheses around the 0.37.
so where's the parentheses gonna be?
Okay, so square root parenthesis,
Uh-huh.
now go 0.63 times 0.37 divided by 500, close
Divide
parenthesis.
by, okay, got it.
Yeah.
Thank you.
I don't want to put the parentheses around the 3.7 because I don't need to.
You gotta go slow. I have to go slow.
Yeah, no, you This is one of these things where we have all the numbers, but we got to know that we're entering correctly.
Yeah.
Yeah. We got negative 0.3, negative 3.7. Okay, so if I go back to my picture, where's negative 3.7? Probably about right here. You've got an outcome that's kind of extreme. Would you agree? A z-score of negative 3.7 is kind of huge in the negative direction. The probability of that being happening is, yeah, 0.000. Yeah, in other words, it's the whole getting struck by lightning while you're inside, you know, taking a shower kind of stuff. This number's really, really far negative. Remember, we said we were going to reject if we were smaller than this. Are we smaller than this?
Yes.
By
Right
quite a lot, though. Yeah, no. That's important. That's important. So, I'm part of the reason I'm doing this so narrow because it's on Zoom. I want to get everything on here. Now what? I got a number. That's my calculation. What do I do with that? We said we would reject if we were smaller than this. Let's write it out. Is it safe to say that negative 3.71 is in fact smaller than this?
Yeah.
Yeah, by a lot. This makes it easy. This makes it really, really simple. My results were actually quite extreme. So now we make a conclusion. We said we would reject the null if this happened. Oh, did this happen? This happened with an exclamation point. So what is our conclusion? Reject the null hypothesis. P is less than 0.63. It's that simple. And by the way, this was actually done in San Diego at that time. I remember because I was teaching statistics and I was like, and I used this example a lot. Now, the 0.63, I'm just making it up because I don't remember what the original claim was, but it was in that neighborhood. I'm sorry, say again.
I'm confused how you got P is less than 3. What you did is you rejected the.
I rejected this.
The claim. You rejected
I rejected the null hypothesis because our results were extreme. Therefore, we're saying this is the truth. That's it. Either you reject the null or you fail to reject the null. If you reject the null, then you're saying the alternative is the truth. If you fail to reject the null, then.
So in the beginning, you have 2 different outcomes.
This is how we started the problem. So in the end, what happens to this? We threw it out the window, right? Was it the whole baby with the bathwater thing? I don't know, something like that. I never understood that expression, but we throw that out. We throw it out. Now, by the way, I'm giving you a scenario that actually did happen. It did happen, and by the mayor and the DA both kind of went into obscurity shortly after all of this. They kind of disappeared. And the DA, that's one of those jobs that you have for many, 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 many years. And we had a new DA fairly soon after because there's a lot of shadiness.
But
how many calculations? You only did one calculation though. So that's
there's a lot of like numbers.
yeah. And this is the whole point of statistics. Remember, this is what the whole lecture was last day. We did the null and alternative and we stated the criteria. We did that for a whole lecture. So you can get used to it. Okay. So this is a scenario. Statistics is really designed to attack scenarios, situations. Okay. So let's do another one. Well, here's the important thing. Yeah, and I said this at the beginning, that the information, everybody has access to the same information. Therefore, everybody should be making the same conclusion. Now, we drew a clear line in the sand. There was no ambiguity in our results. Do you agree? We drew a clear line in the sand, and that's exactly what just happened. Okay? Now, let's say that so let's do a new problem. All right. So I'm going to do something on the other side now. I'd say that we'll say we have a short order cook. Okay. Now, Biff is a. I love you. Some of my favorite names. I have Biff and Skippy and Muffy and Buffy, and I like to use them a lot in algebra.
Yeah.
And people always ask me. I actually knew a Muffy, Buffy, Biff, and Skippy, and they're like boyfriends and girlfriends. They were the ones that wore the sweaters around their neck, and they all talk like Thurston Howell. And I mean, like sickening stereotypes. Yeah, but girls' legal names were Muffy and Buffy. Those weren't nicknames. Biff and Skippy, those were their legal names. Skippy was like Skippy the Third, by the way. Yeah, who would do that to their child? But anyway, yeah, they were.
Started on names.
But yeah, right. So Biff is a short order cook. He says at most 10% of his orders are burnt to a crisp. Okay, yeah. It's not at most 10%. You know, there are days when
He's a better cook than me, though.
there's days when only 5% of his orders are burned. There's some days maybe nothing's burned. He says at most 10% of his orders are burned to a crisp. Problem is, you've gone and ordered food from Biff a lot of times recently, and you're thinking you sent a lot more back than 10%. Okay, so Biff is making this claim. Biff's got his own website, you know, Burnt by Biff, I guess you can call it whatever you want. And he says on his website, hey, come to me, I'm going to burn less than 10% of your food. Okay. You're going, you know, I don't know. I don't know. So the exact same problem. Let's test this claim. He says at most 10%. So it's still a one way. It's still a one-tailed. So P at most is what in inequality? Less than or equal to. That has to be the null because it's got the or equal. So therefore, what's the alternative? Greater than. Now, it's not that you want to, you know, throw Biff under the bus. You're just like, well, Biff, I think you're not that good of a cook, and you know, not that 10% is a really good number, but you're thinking it might be a lot more than 10%. Okay.
An amazing cook, but he just burned it.
Well, we had Biff eventually left and worked for that Cajun restaurant. So I don't know about you guys. At my house, that's always been the joke that when something's on the grill for too long, we say we made it Cajun. There are people that actually, that was a 90s thing, that Cajun meant it was burnt, and people would pay extra money for their food to be burnt, not understanding that was just a gimmick. I'm pretty sure I've had Cajun food. I've been to New Orleans, and
Likes everything.
He loves burnt food.
but it's actually very unhealthy.
It is.
Carcinogens. I've been to New Orleans. I've eaten Cajun food. You know, I've been to Bourbon Street. And nothing was burned. It's spicy. Mm-hmm. They don't burn food. And so when we talk about Cajun food, you know, it's like burnt, you actually on the, you know, burnt fish or burnt whatever. It's like, what? But they burn it in the right way. Anyway, so Biff is training to be a Cajun chef, let's say. So here's the situation. You want to test at the, let's this time say 0.01 level of significance, just so we can do a different number. Okay. Well, how do you test initially? Well, you have to collect data. So the next thing we're going to do, this is given. This is given. The test at this level. We did this because we're looking at the situation and we're stating this is what the problem is. If we don't state this, then we don't have any conclusions to make. So we've got to state a null and an alternative. So at the end of the problem, we can make a conclusion like reject the null or fail to reject the null. We actually have to have a null hypothesis. Now, at the O1 level, now let me draw the little picture. What are we going to reject this time?
0.7.
But what are we going to reject? The extreme right. The other problem, we rejected the extreme left because it was a less than. This, we will only reject the extreme right. So it's got to be overwhelming, like way more than 10%.
The two, and when it's equal or not?
Versus not equal, exactly. Because if it's equal versus not equal, we would have rejected either extreme. Well, that'll be our next example. Okay, so everybody cool with this? So what is my magic number? What is my line in the sand? What is Z of 01?
2.326.
2.326. Do not memorize these, just know where they are. We know the 196, but that hasn't come up yet. That'll probably be the next example. So therefore, what will we reject? We will reject the null hypothesis if our measured value of Z is what? Greater than 2.326, because we're looking at the far right this time. You don't have to, but you should always do the picture, because then it makes it very clear. If you said reject if I'm less than this, then I'm rejecting 99% of all outcomes. No, I only want to reject the extreme 1%.
That's a silly question. Like, you're never rejecting the bottom one, right?
You're rejecting or failing to reject the null hypothesis only. The null hypothesis is my assumption of not guilty, if you will. When you go on trial, we're assuming you're not guilty, and we're letting the evidence tell us otherwise. And if the evidence isn't overwhelming, then my conclusion is not that you're innocent, but that there wasn't enough evidence to prove guilt. So you're off the hook. Everybody understands that. We don't conclude innocent. We just conclude, the other one. Yeah, it's Robert.
How do you find NX?
How do you find what?
How do you find NX?
And you're going to go out and collect the sample. Yeah. So, all right. So you've been to Biff enough to say, I think he's exaggerating. Okay. So now you're going to go out and collect your sample. Now, by the way, the sample can be you, because you eat there all the time. But probably better to sample other people. So you went out and you collected a sample. Let's say you didn't have all year, so you collected 37. And what are we going to call a success? That they burnt the food. Because remember, that's what we're counting. We're counting how many people had their food burnt.
X.
So our X will be the number of who had the food burnt, not who had a good meal. Remember, what are we testing? Burnt food. We're trying to figure out who got the food burnt. So we're going to call a success somebody whose food was burnt. Because I say, was your food burnt? Yes or no? You said yes. Okay, another tally on my sheet. You got it? So we went out and collected, and we got, let's say, 3. Again, we're only asking 37 people. And we got, we got X equals 3. So what is our measured probability? 3 over 37.
Make that to a decimal.
I would leave it as a fraction only because it's not a terminating decimal. When something's a terminating decimal, entering it in your calculator is probably easier than the fraction. But that's not a terminating decimal. So if I round it off and I enter the rounded off number, I'm compromising my final results. And the problem with that is, what if it's a really close call and I'm on the wrong side of the line because I rounded off prematurely? Ooh. Yeah, you're doing everything on a calculator. So we'll just use that. In the last problem, I wrote it as a fraction, even though you probably all entered the decimal. So in general, say, p hat is always a fraction. I would have been better off asking 25 or 50 or some nice round, number but that's what you did. In real life, it doesn't always come out perfect. Okay, so now how do I calculate my Z? My Z star it's p hat minus p over the square root of a bunch of stuff. Now, what are we assuming? We're assuming that the null hypothesis is the truth. But we have to use the equal. This is why the null has to contain the equal. So we're going to assume that he burns exactly 10%. The fact that it could be less is okay, but we got to have a number. What is the number we're going to use as the truth? Whatever the equal is. That's what we're going to use as we're going to assume that's the truth. So we're going to use 0.1 as our P. Now what goes in here? The assumed P, Q, and our N was a 37. So if P is 0.1, what's Q? What's what? 0.9, right? Because they got to add up to 1. If nothing else, these two numbers have to add up to 1 on top, don't they? This is the assumed P, not the measured P. This is the assumed P. So let's do this whole calculation on our calculator. So again, using parentheses at the right place. So parentheses on top, divided by square root, and then parentheses on the bottom. 0.1 times 0.9 divided by 37, close. Tell me when you get a number. Remember, this is a Z calculation. You can go as many as you want, but since it's Z, we always go at least 2.
I got -0.30.
Okay. I'm going to wait for everybody because I need you all to get the same number. Got it? Nice. Oh, I love the readout. Then you know you did it right. Rogers does that too.
It does, but I did that one first.
Okay, so now say that number divided by,
Okay.
and then square root parentheses. And now 0.1 times 0.9. No parentheses, just times 0.9.
Okay, let me go back.
No. That parentheses is fine.
Okay.
Just 0.1 now hit times 0.9.
Oh, okay.
Divided by 37.
Divided by, I always forget that.
And now close the parentheses.
Okay.
No, it's got to close the parentheses after the 37.
Okay.
Okay. See, now that's everything in your room.
That's it.
Now hit your equals.
I can do equals there.
And what do you got? It didn't like that you put, I think you moved your parentheses too far.
I did. Okay, I'm gonna redo it.
You had everything right.
Uh-huh.
But now that square root, remember, it's got to include the 37.
Okay.
It makes so.
Make sure I get that.
Yeah.
Okay.
Are we all getting it? Did you get negative 0.38? Yeah. Okay. Juniors get negative 0.38. Now, I want to make sure you guys absolutely have confidence. This is the only calculation in the problem, so I got to get it right. Because my conclusion, Biff's future is hanging in the balance. If you hit a wrong button and you have a miscalculation, you do realize, you could be throwing Biff under the bus unnecessarily.
For these problems, if they're some of our code or text, we have to figure out the M and X ourselves or everything.
No, that's given. Everything's given. Sure. Well, there's nothing to figure out. The situation is this. I'm saying you're the statistician. You went out and you collected the data. You control a few things in the problem. You cannot control what people are going to say. You just are counting what people are saying. So you got it?
Okay, I got up to this point. How do I?
Okay, you're closing the parentheses, so go back one.
Okay.
You still don't have the divided by 37. Now,
Yeah, I didn't do that one.
Divided by 37.
So now do the, okay.
Still got to be inside the parentheses. Divided by 37. And now close your parentheses.
Okay.
Now hit equals.
Oh, okay.
Before, what you did was you scrolled out and you took the parentheses out of the square root, so your calculator didn't know what you were trying to ask.
Okay.
All right, now look at this answer. Okay, let me go back to my picture. 2.32, sorry. So we're going to call any z bigger than 2.326 extreme. Agreed? Our calculated z is about right here. Are we rejecting the null hypothesis? We're going to reject if our calculated z is bigger than 2.36. Our calculated z is to the left of 0.
No.
I'm not going to reject the null. In fact, this is kind of overwhelming evidence that he is actually telling the truth.
Oh.
Well, I still think 10% is a lot of burnt meals, but
Yeah,
he says he burns at most 10%.
but he's right.
You're on this side. You're saying, you know what? First of all, the first thing is you fail to reject. That's the correct conclusion. Fail to reject the null. Now, I have a lot of people in stats, they do a lot of lawyers speak, and they don't want to commit. They'll say, well, based on the evidence, there's none of evidence to conclude, and they'll start giving all this long list. This is an example where, you know what? You went out and you collected a sample, and that sample was way less than 10%. Your sample is really kind of overwhelming that he is telling the truth. So a perfectly reasonable conclusion would be he is less than 0.01. Not there's not enough evidence. No, that evidence is pretty strong that he really does burn at most.
Why didn't you look at your Z-value?
We did. That's our line in the sand.
Remember last one you.
Oh, I wanted you to see how extreme it was.
Oh.
Okay, hold that thought. There isn't we are going to look that number up, but we have to give it a reason to look it up. Okay, so is everybody cool with this? This is our conclusion. We failed to reject the null, and in fact, you can say, I believe the null is actually true. That's a completely reasonable thing because the data came in not close. The data came in that, oh, he really did burn less than 10%. Wow. So Biff has a job for at least another week. So you were ready to toss Biff, and so he's getting at the job at the Cajun restaurant down the street because he's so good at burning things. Now, there is one more piece of the puzzle after all of this that sometimes is very, very helpful. And it's, let's see, I need to erase some of this. There's something called the p-value. And this is I wish we could have used a different letter because too many P's in this problem. A p-value in simple English is if the null is actually true, regardless of what your result is, whether your result confirms the null or whether your result rejects the null, your result could be extreme in any direction. Regardless of what your result is, the p-value is if the null is true, then what is the probability of a result as extreme as yours or more extreme? That's what we're now going to look up in the table. So if the null hypothesis was true, then the p-value would be what is the probability that we are actually this extreme? Now, we are only going to reject in this direction, okay? So in this case here, this is not extreme, but we would say go towards the rejection. So what would be, if the null is true, then our p-value would be the probability that our z is, what did we get, negative 0.38? Remember, we're calling that extreme in that direction. So what's the probability that z is greater than negative 0.38? That we're going to look in the table. And I'm going to make some sense of the next couple problems. So that will be, since it's a greater than, it's going to be 1 minus what?
I need a break, Professor.
Oh, well, let's look up the number first. Right? So negative 0.38 is what number?
0.3530.
And so that number is 6480. In simple English, if Biff was actually telling the truth and the null is true, then we can expect results this extreme or more almost 65% of the time. And you're good with that. You're good with that. Yeah, let's take a really short break. We don't have a lot left to do, but then I also want to get to the quiz questions, at least set one of them up. Okay, we have one more example to do. We have the equals versus not equals.
For the probability, you're looking between
So I'm looking at my result and in the direction that it would have caused me to reject it. In the previous problem, now I want to go back to the previous one. In the previous problem, our z was negative 3.7. It was something ridiculous, right? Mm-hmm. By the way, negative 3.7 is a ridiculous z. It really is. So in the previous problem, our z value was negative 3.71, I think. So the question is, if the null hypothesis were actually true, what is the probability of a result this extreme or more? And when you looked it up in the table, wasn't it 0.0001? So what's the probability that our z would actually have been less than this? They're saying it's about that. It's actually It's actually smaller.
I'm looking at the picture, because the picture does help me. Because,
we rejected in the left on the first point. So in other words, we were going to reject it here, and our results were way more extreme than that. It wasn't even close. So we're saying if the null were true, if the null were actually true, then just how ridiculous is our result? If the null were true, we would get results this extreme less than this. That's why you have real confidence that the null was not true on this problem, because that was so absurd. That was so absurd. So sometimes the p-value helps you make sense of, it doesn't change your conclusion. It helps you sometimes make sense of your conclusion. Whatever the level of significance is, if your p-value is smaller than that, it's because you reject it. That's an absolute. So if your level of significance is 0.5 and your p-value is smaller than 0.5, it means you rejected it because you were way in the tail. Oh, but if your p-value is bigger than 0.05, then you wouldn't reject it. So if your p-value, by the way, a lot of stats classes, they only use the p-value. They calculate the p-value if the p-value is bigger than the alpha versus smaller than the alpha. That's how they make the conclusion, and that's correct, but it's a little confusing at times. That would be maybe an upper level class. You guys need to get up, move around. You're just sitting there.
the fact that I feel like I'm tired of the already, and it's really confusing.
Yeah, well, we're to that point of the semester where it's, there are no more days off and there are no more short days, but at least it's light later. All right, I have a new problem, okay?
Can we do the Friday yet? Yeah. I got mine.
Did you say prom?
Yeah, we're going to prom. We're fresh out of high school.
Can you do that?
We early graduated. We early graduated, so we're able to.
Oh, okay, okay. My son just went to prom Friday night. He's a senior. Was it Saturday?
No,
Saturday.
Saturday.
His prom was on Saturday. He just had a prom. He'd never even been on a date, and he just has a girlfriend like in the last month or so. And so, of course, he took her, and we still haven't seen hardly any pictures yet. My wife read him the riot act, and it's like, I want pictures. And he's got a crappy cell phone, so he's waiting for his friends to send him all the pictures.
Yeah, we have prom in 2 weeks.
You understand this one? So you guys know what a tackling dummy is? In a football, it could be on the sled. So Robert has a legendary reputation on the football field of making tackling dummies scream, even though they're inanimate objects. He hits them so hard they actually scream. So apparently, Robert puts it out there on his social media page that exactly 40% of the time that tackling dummy screams when he hits it. Okay. But, Salvador was watching a practice recently. He's like, I was kind of loosely keeping track, and I don't think 40% is correct. Now, it could be higher. It could be lower. He just doesn't think that number is correct. You guys with me?
Okay.
So at the 0.5 level of significance, we're going to test this claim. And I'm already telling you. So basically, Salvador was the statistician. He went out to a few practices, watched Robert hit the tackling dummy 50 times, and he heard 23 legitimate screams. Now, he's certain those screams came from the tackling dummy, but that's the whole point. So now we need to set up our null and alternative. We need to set up our criteria for rejection. That does not require any form of calculating or anything. That's interpretation from the given information. So that's why we want to be correct So our known or our alternative. Now we're testing an equal versus a not equal. He says exactly, not at most, not at least. That's why I underline exactly. He says it's exactly 40%. Okay, so what is our null? That P is exactly 0.40. What is our alternative? It's not 0.40. So in terms of a picture, what will cause us to reject now? The extreme this way or the extreme this way? This, by the way, this is the same mathematics as if we're trying to test if a coin is fair. It doesn't matter if it has too many tails or too many heads. We want it to be exactly 50-50, correct? So we're going to reject in either extreme. So this is called the two-tailed test. Okay, so if it's a two-tailed test and my alpha is 0.05, that means there's exactly 2.5% in each tail. That's a different Z then, isn't it? So now I'm not going to look up Z of 0.05. I'm going to look up Z of 0.25 because the total tail is 0.05. So this is the Z we use in a confidence interval, in other words. This is the most common Z, certainly for confidence intervals. I know some of you know this one.
1.96.
1.96. So in this situation here, again, the total tail probability is 0.05, but I have half of it in each tail. That's why I'm not looking up 0.5, but 0.25. So I will reject in the high end or in the low end. Now, remember, you're setting up your criteria before you take your sample. You don't set it up after the fact. That's kind of cheating. Let me take my sample, then I'll decide what I think. No. I decide what I think, and then I go and take my sample. So what will cause rejection? I'm going to reject the null hypothesis if my calculated Z, how do I state the left tail? Well, that'd be a negative 196. The right tail would be a positive 196. So if it's what? Less than negative 196? Or what?
Or if it's more.
Or bigger than positive 196. Does that make sense? I'm going to reject it at this end or this end. So, by the way, when I do my calculation, I'm only going to get one value. So the question is, when I do my calculation, does my value fall in the bulk, or does it fall into one of the two tails? And that's how I make my conclusion. But it can fall in either tail because it's a two-tailed test. We're doing an equals versus a not equals. In the first two examples, we did one tail only.
Yeah.
Okay. So this would be more like another way I like to think about this. Does anybody have a bathroom scale at home?
Yes.
Is it accurate?
No.
That's one of those things that scales are going, I don't know if my scale is accurate or not. But if I say it's accurate, but you don't know if it's too high or too low, and you don't care if it's too high or too low. You just want to know, is it accurate or is it not accurate? So what I do, I have a bathroom scale. It's funny, I also never used to weigh myself. I literally only when I had physicals. I don't weigh myself during the course of the year, but my weight doesn't fluctuate. My weight is literally the same every day of the year, all year round, no matter what. I know it's weird.
That's impossible.
I weigh myself roughly at the same time every morning, and I've had the same weight for every day in 2022.
What's your secret?
I don't eat junk food. but here's the point. Anybody ever weigh themselves at the gym?
It's always different.
And why is that one always ridiculously inaccurate? I'll tell you, because not hundreds of people use it, but everybody, when they slide, I'm talking about the ones that slide in the balance ones, they always leave the weight on there. So over time, it creates an imbalance.
Oh.
So when you set it to 0, it automatically tips. You go, wait a minute, it should be perfect. You guys know what I'm talking about?
I do.
The gym scales were very, very expensive. They're the slider balance ones, but because the previous person always seems to leave the weight on there, that causes it over time to malfunction. That's a reality. So it would be the similar thing where I say, is your scale accurate or not? Not accurate would mean it weighs too heavy or too light. Either way, you're saying it's unacceptable because I want it to be exactly right. So that's what we're doing here. Robert says he's exactly 40% of the time. So we're saying, well, if he's way above or way below, we're going to say you're inaccurate. But if our results come in really, really, really close, then you're probably telling the truth. Does that make sense? But we're going to reject it in either direction. So we went out, or Salvador did this for us. He went out, collected the data. By the way, this for P, this is really simple. It's you collect your data, and how many successes do you have? It's always the same thing. Roz shot free throws. How many did she shoot? How many did she make? You ask people a yes or no question. How many did you ask? How many said yes? So when you're doing tests on P, the calculations are really, really simple because there's just not a lot going on. You're not measuring things. You're just, it's a yes or a no. So in this case here, what is our P hat? 23 over 50, which in this case is a terminating decimal, isn't it? So this is one of the times I will rather use the decimal because it's easier to enter. If it were 23 over 51, no, I'd leave it as a fraction because it's, infinite, okay? All of this is done before you collect your sample. And now you're saying, based on my sample, I can make a simple conclusion. And there's no opinion, right? There's no, well, I think it should be this. No, this number is going to speak loudly. There's a line in the sand. I'm either going to be here, or here. That's it. And I just got to read it correctly and calculate it correctly. And for us, that right now is probably the biggest challenge, isn't it? Just making sure we hit the right buttons. That's why it's so critical that you keep practicing. So our Z star, our calculated Z. And the reason, I use Z star is because our line in the sand is also called Z. And I don't want to confuse the two. That's the line in the sand. And again, I don't need you to draw the picture, but you probably need you to draw the picture so that when you get your calculation, it agrees. Your conclusion agrees with what the logic of the picture suggests. Is my picture perfect and flawless and computer generated? Yeah. No, but it's pretty clear what I'm going to reject there or there. And I made it real. I even wrote the Z values and that kind of thing. So our calculated Z is 0.46 minus what? This is what we assume to be absolute truth unless evidence says otherwise. So I use 0.40 over the square root of 0.40. What's the Q? 0.60, because it's got to add to 1 over 50. Now let's do that calculation. And by the way, you don't have to do very many problems to realize you're doing the same calculation each time, aren't you? And so where to put the parentheses is no. This is your friend. You just got to talk nicely to it though.
Parentheses mixed up because you'll write it there, but then
right. But when you enter it, because think of it this way: when there's stuff going on, you got to have the parentheses because your calculator doesn't know what's the numerator. We wrote it that way, but when you enter, you're entering it left to right on the calculator. So by putting the parentheses around the top, you're telling the calculator, oh, that whole thing is my numerator. Because then when I hit divided by, your calculator will say, okay, the whole thing.
Calculator, use parentheses on the top.
Yeah, because you have stuff.
I get confused if it's written this way and then we enter different.
On the top, what you did earlier was correct. You said, let me go ahead and calculate the top and then I'll start the problem. That's legal. You can always do that.
All right.
But no matter what, you have to have parentheses on the bottom because you have 3 things going on inside the root.
Yeah.
And if I don't use parentheses, my calculator doesn't know I mean all 3 of them are in the root. So that's why when I'm entering it, the only parentheses by the way, why do I put parentheses when I'm writing it?
You know the difference.
So I can tell which number is which. Now I put parenthesis, this number times this number divided by this number. Now close, so now my calculator knows exactly what was inside the root. Well, you've gotten it right so far.
0.86.
All right, so 0.866, so probably 86 or 87, okay? Now, where does that number fall, by the way, in my picture? That's about there. Do you agree?
Yeah.
Am I even close to rejecting?
No.
Not really, no. You're not really very close to rejecting. So what's your conclusion then? What's the language we're going to use? So here's the way I like to think of a hypothesis test.
Yes.
Did you get it? Good, good. Here's the way I want you to think of a hypothesis test. Robert's making this, and Robert went on Twitter, where he's saying this, and you're going, wow, I've heard about this guy, and his name might get called Thursday night at the NFL draft and all this stuff. And Robert's saying this, but I know that Salvador is challenging it. And so when all is said and done, we're holding a press conference. And we're going to announce to the world what our findings are. English should be simple. And it cracks me up. I will have people say, all right, based on the hypothesis testing, there's not enough evidence to conclude that the null hypothesis is not true. Therefore, the alternative is a reasonable assumption. And I'm like, so is he guilty or is he not guilty? Please do not be a lawyer and start using, I have a close friend who's a lawyer. We always joke, when you ask a question that he doesn't really want to answer, he goes into lawyer speak. And at the end, I'm going, it was a yes or no question, and I don't know what you just said. So, first of all, do we reject the null or do we fail to reject the null? We fail. We're not even really very close to rejecting. So our first conclusion, I'll raise this up here. All right, so our first conclusion is fail to reject the null hypothesis. Now, the evidence came in at 46%. He claimed 40%. That's a little bit of a gap. So this is your own opinion. Do you want to say that, yeah, Robert's telling the truth? Or do you want the safe out just saying there's not enough evidence to reject? So it's sort of like saying, you know what? We found him not guilty. But we're not sure if he's innocent, but we know he's not guilty. It's probably safer to just say, we know he's not guilty. So probably the safest one would be to say there is not enough evidence to conclude that P is not.
But you have probability.
See, here's the thing. When you reject the null, you're saying that the alternative is the truth. You rejected the null, you're saying they are guilty. That's it. That's absolute. There's no gray area there because your evidence made it clear. When you reject the null, that's because the evidence was overwhelming. So the alternative you're stating is the truth. It's basically saying, I'm rejecting the not guilty assumption. You're guilty. Okay. Doing the alternative is like saying, we found you guilty. We're saying that is now the truth. Okay. And the language is real simple. When you fail to reject the null, it's because you weren't out here, but you're saying, you know what? I don't know if the null is the truth or not the truth, but there certainly wasn't enough evidence. Okay. In the football game, there wasn't enough evidence to overturn the call. When they say that, are they saying they were absolutely correct in making the call? No, they're just saying there wasn't enough evidence to go the other way. We could have still been wrong, but it had to be overwhelming to go the other way. So the safe one is, whenever you're watching any game where they challenge it, they'll come out and say, the call stands. That doesn't mean the call was right. That just means there wasn't enough evidence to overturn it. They'll say, the call has been overturned. That means we found you guilty. That means I rejected the null. That's the exact same thing. But every now and then, they'll say the call was confirmed. They use that every now and then. That means, no, we got it right. Absolutely, the null was true. Every now and then you hear that one. They are innocent. Okay, so, yeah.
But it's bigger.
But it was in either direction. That's all that mattered. So now we're going to do the p-value. The p-value for the two-tailed test is a little bit tricky. It's a little bit tricky. I'm going to leave this up here. This was our calculated C. So when I'm saying, what's the probability of a result this extreme or more, I'm always going towards the tail, okay? So my p-value is the probability that Z is actually bigger than 0.87. But here's the confusing thing about a p-value. When it's a two-tailed test, I say, what's the probability of a result this extreme or more in either direction? So in other words, 0.87 or more this way, literally, or negative this way. So what we actually do is we multiply it by 2, only in this situation. because we would have rejected with either extreme. With either extreme. Now, can you look up this number? Yeah, let's look that number on our table. So 0.87 on my table corresponds with a probability of 8078. But that's a greater than, so this is 1 minus. Agreed?
Yeah.
Now, but I want to go 2 times this. And by the way, this is why I really like the p-value, because it makes things make a little bit more sense in the end. Let's calculate this on our calculators. Tell me exactly what that is. You can just do 1 minus and then times 2.
0.19.
What times 2?
Oh,
I'm sorry, 38.
4.
Okay. Here's the way to make sense of this now. All right. Robert claims he makes, or that he makes exactly 40% of all the tackling dummies cry, scream, beg for mercy. We went out and collected a sample, and the sample was 46%. If Robert is telling the truth, a result this extreme or more extreme is still going to happen this often. Oh, that's pretty often. That's more than 1/3 of the time. So in other words, this is actually kind of strong evidence to say, you very well may have been telling the truth. Now, if your p-value is microscopic, then you're saying if he's telling the truth and I get a microscopic p-value, you're saying then if he's telling the truth, this result is only possible that often. That's not very often. I don't believe you. But if you're telling the truth and 0.4 is the right answer, then I can still get results this extreme this often. Think of a coin flip. If you flip the coin 10 times, are you going to get 5 tails? You might get 6 tails, you might get 4 tails, you might get 7 tails, right? That's not 0.5. Oh, okay. So if the coin is fair, it's 7 completely outrageous? No, but if you calculate the p-value, you get a p-value probably 0.2 or 0.3, saying, oh, yeah, I can still get results that extreme even on a fair coin, because you're not going to get perfect. If Robert really does make 40% of the tackling W scream, that means if we continued to do this over and over, we kept experimenting, then over the long run, we would see 40%, wouldn't we? Does that mean every sample is going to be 40%?
No.
Does it mean every time you flip a coin, exactly half of them are going to be tails?
No.
No, but over the long run, remember law of large numbers? That's why if you said, you know what, this is reasonable based on this p-value, that's a pretty good p-value. 38% of the time, he can get a result this extreme or more extreme if this is the absolute truth. In other words, every time you go out, are you going to get exactly 40% every single time? Think of every 5 times you get the tackling dummy, you might only get 1. And then the next 5 times you might get 3. Oh, okay. Because things can change each time we're doing sampling. So I want that to make sense. Now, if you have time to stay, I'd like us to look at the first problem on today's quiz. The problems themselves, there's nothing difficult about it. It's this structure. Now I've asked you 2 questions on the quiz. They're P's. Next day, we're going to do tests on mu, on the mean. And it's pretty cool stuff because it's exactly how it's done in real life. We like real life. We're into the whole real life thing. Is that coming up? Let's see, a little bit true. Oops. I must do it wrong.
Yeah, but I forgot to so I'll just
Don't forget, give me your latest quizzes. Also, there are graded quizzes up there. People don't always remember. Obviously, you looked at the key, you already know what the right thing is, but still. So what is today? Today would be
20.
No. Driving nuts. The other day, students suggested I just tie my briefcase to it. So right when I started tying it, it grabbed. There we go. I have one that we actually spent a couple minutes just up and down, up and down, up and down, and it just won't work. So why is this? Oh, it's not a PC.
Are your classes in here?
No, I only have one class. Most of my classes are on the other side, on the fourth floor. They're all on the fourth floor too. All right, so here's the situation. Let me turn off that light. All right, so Isaiah is an archer. And he shoots the arrow into the target. And he says he makes it 40% of the time. Now, is he saying exactly 40%? At least for good. Here's where we have to read it. He didn't say exactly, but he said, I make it 40% of the time. If he actually goes out and makes it 50% of the time, you're not going to say he's lying. If he goes out and makes it 10% of the time, you're going to say he's lying. Oh, he's saying I make it 40%, but better than 40% would be fine. That's why it's a greater than or equal, it's a less than or equal. What's he claiming? Greater than or equal to 0.4. So when you state our null and alternative, this should look real familiar. I mean, we just did, right? This is like very much like the Qualcomm, first problem we did today. And I'm saying at the O1 level of significance also, so you have to make sure you're looking at the right magic number. So H0 is what and H1 is what? So what is your H0? So what are you testing, by the way? You're testing P. So what's your H0? Well, H is not H0 is a sentence. H0 is not a value. Your null hypothesis is a statement. It's not a, and kind of need a variable in there.
Professor, I thought it would be at this symbol at least.
Yes, that's right.
And so we'll go like this.
Greater than or equal to.
That one.
Yeah, and so what's left would be less than.
Okay.
Because that's,
okay.
Yeah, that would cover all numbers.
So okay.
Yeah, so therefore, what he says, he makes it 40%, clearly at least 40%. So it'd be 0.40. Huge. Yeah. Don't say H0 is greater than or equal. That doesn't make sense. H0 is not a number. H0 is the statement. My null hypothesis is that Isaiah claims that he makes at least 40% of his free throws. That's what the null hypothesis is. The alternative is now he makes less than. So in symbolic form, we can just say P is greater than, P is less than, keep it easy. Now, what is your criteria for rejection? Now we've done this at the O1 level, and it's a one-tailed test. So here's where drawing a little picture, are you going to reject in the left tail or the right tail? How do you know? Because your alternative is less than. That's how you know. Yes, exactly. Everybody understand that? Your alternative hypothesis is a less than. So you're going to reject in the extreme left. So when you look up, yes, you're going to reject in the left tail. So when you look up your magic number, that does affect. I'm going to reject if I'm bigger than a positive number or more negative than a negative number. So what is your magic number? 2.326. 2.326. Well, Robert memorized the whole Z table. So and he knows the first 1,000 digits of pi. What's next in the encyclopedia? He's got a lot of time on this.
I see. Got this.
So now that's the magic number. So what's my criteria for rejecting?
I'm doing the whole problem up there.
Oh, okay. Just do one, because some of the stuff's going to be done. So state the criteria for rejecting. I'm going to reject if what? It's one of these kind of statements now.
Okay.
Reject and
Okay, got it.
You don't want to do that.
So you want to get the negative. Reject what? If your calculated Z is bigger than or smaller than something, this is where we use the Z star. Reject if your calculated Z is.
Oh.
Well, it has to be. What has to be? Well, draw a picture. What is going to cause you to reject? You're going to reject in the extreme left hand. Agree? So this one. Okay. So if I go like this. Now, if I'm doing this, if I go, so what's that? The positive would be better, but I'm going to reject the better. So therefore, that's because that's what my inequality tells me. Oh, if that were greater than, then I'd be negative. So this is why drawing a little picture, except that's right, so I word negative.
Okay.
If I'm not
Other way.
here's what I'm just doing. That's 0. That's negative 2.326, isn't it? And that's, think of it this way, and that's positive 2.326. But I'm not rejecting the right tail, I'm rejecting the left tail, which is why it's got to be smaller than the negative.
Okay.
Because if you said smaller than the positive, then you're rejecting almost
all of it.
Everything. So that's why it's got
it's got the other way. Okay.
Yeah, that's if you look at a previous example. Does that make sense?
I see. Okay.
So if it's less than, it's less than the negative. If it's positive, it's greater than the positive. Because we've got to have extremes. If I have my inequality going in the wrong direction, then I'm going to reject everything. I'm going to reject good things.
That's true.
And that would be, well, that would be bad. Don't reject good things.
Find the value of the test.
Oh, yeah. Now that's the Z. By the way, that's kind of a generic term. By the way, everybody pay attention to this. I say find the value of the test statistic. What does that mean? Well, there are exactly 3 test statistics. Okay. Say they are? Yeah. But remember the chi-square? Oh, that's the quiz you just turned in today. That was your test statistic. Oh, we're doing Z.
Okay.
But that's whenever you do a hypothesis test, you're going to do a single calculation. Z is the most common. So Z would be called our test statistic.
Okay.
But there are other test statistics.
So that would go for this reject equal because alternative is less than.
Okay.
Okay.
How did you get through? Oh, you calculate reduce this as
Yeah.
Oh, okay. Like, how did you do that? Okay. Yeah, so I want the decimal. So you're saying my calculus is negative 2.6, but negative 2.6 is on the other side. Yeah. So therefore, it should make my conclusion easy. That's Z star, if you will.
Okay.
That's the one I'm calling Z star. Now I have an interesting situation for you. Which one? So now we're going to do the calculation.
Do all this.
And that's given. So what's my N is 200. The X is 62. Okay. And the P that therefore is 62 over 200.
Yeah.
And that's the guy that's going to go in that position.
Okay.
Remember the truth.
Oh, and this is going to be the calculation on all this will be this.
Right. We're saying we believe 0.4 is the truth. So 0.4 would go whether 0.3 is in this case.
Okay, got it.
Now, let me ask you a question. When you reject the null hypothesis, it's not a question of degree. It's you reject it or you didn't reject it. It doesn't matter how close you are. If you reject it, you reject it. Do you agree with that? Here's the way I always like to explain it. Okay. I have a lot of kids, and anybody here have siblings?
Yes.
Okay. Did you grow up? You know King of the Couch, right? Everybody knows King of the Couch. You know, you basically fight tooth and nail because you don't want to fall into the shark-infested lava. In my house, it was shark-infested lava. Everybody understands this concept, right? You King of the Couch, and it's some people have it's hot lava, some people have shark-infested waters. In my house, it was always shark-infested lava. That's the scariest stuff around. Okay, so King of the Couch, you know, I have boys and everybody wrestles and fights on the couch. So here's the thing. There's a line in the sand right here. You created a line in the sand. You're over here. On the other side of the line in sand is a 1,000-foot drop into shark-infested lava. Okay? So when you're doing your test statistic and you're doing your Z calculation, does everybody understand? You're either going to end up here or on the other side of the line. You got it?
No.
Now, does it matter? But I barely went to the other side of the line. I barely crossed over the line. You know what? Whether you barely crossed over the line and fell into the shark-infested lava, or whether you were rocket launched out into the shark-infested lava, you're still in the shark-infested lava, and you were eaten up and burned and everything. It's not a question of degree. when you reject the null. You just reject the null. Okay. So some folks will say, well, I almost found them not guilty. No, if you found them guilty, they're guilty. There's not degrees. They're guilty. So you got something at that end. No, we're not doubling this one. We only doubled the two-tailed test.
Oh,
so this would just be, and since you're on the left side, it's just 0.047, by the way. That was the p-value.
I should okay.
No, p-value is a probability, so that's kind of big. Now the two-tailed test we doubled.
Okay.
This is not a two-tailed test. This is a one-tailed. So you're just looking straight. Yeah, that p is definitely increasing. It's not a question of degree. I rejected the null, therefore we're saying that is the truth. Yes. The p-value would be that. Now, you notice that's less than 0.001, or 0.01. When you calculate your p-value,
it's like checking your answer.
It's like checking your answer. It's saying if the null were true, how likely is my result? My result's happening this often, which is way less than the 0.01 level of significance.
I just wanted to know.
Well, how would you write the rejection?
How do you write the rejection? You say reject null. Therefore, when you reject the null, what are you saying is the truth? The alternative. Reject the null. You can use words. You can use words. Well, Isaiah says he makes at least 40% of the shots. You can say he makes less than that. Yeah, but you're holding the press conference later on today. You get up to the microphone, all the people are standing there with the cameras are waiting. Null is always whatever is equal. You rejected the null, so there's only one other thing. The other thing. That's not really. There's no gray area there. Now, when you go up to the mic later on today, you say, "I rejected H0, P is less than 0.4," and then the audience is going to look at you with a blank stare and blank. Isaiah claims that he makes this percentage of the time, so maybe your conclusion ought to be Isaiah makes less than that, something like that. You know what I'm saying? It's okay to use words that say the exact same thing. Again, the reason you want to draw a picture is because then when you do your calculation, you can look at your picture and go, okay, yeah, I see why I made that conclusion. It's really obvious. I fell into the shark-infested lava, in other words, and I'm done. Does that help? Now, some of you guys came in a little late today. We were talking about today's lecture and Thursday's lecture is the last material on the last exam, and probably the two most important lectures overall for a stats class, because this is what stats is all about. Stats is about making proper conclusions based on evidence, and hypothesis testing is the most common thing we do. We're going to look at other examples. Next day, we're going to look at things like products. Like there's a product on the shelf at the store, and they say this is what it is, but you're thinking maybe that's not the case. You know, maybe I'm being shorted. Maybe there's something going on. How would you actually perform that sort of test? And so if you guys look ahead, you'll see the question, okay, that makes perfect sense. And it could be something as simple, my scale. I think my scale is off, but I don't know in which direction. You know, so I had a whole bunch of people weigh on one that I knew was accurate versus mine, and you know, I came up with it. There's a lot of ways I can test things. So we're going to test means next day, not P's. All right. So that, where does that fall?
That way.
So therefore, that's why the picture is useful. Okay, I fell in the shark-infested lava. Therefore, now the p-value is what is the probability of a result this extreme or more extreme? So what's the probability of getting a z-value that is smaller than that? And then I can look that up in the table. So the p-value, going back to this picture, your rejection criteria was negative 2.326. That means there's 0.1 in this tail. My outcome is actually this. So I'd like to know, what is that probability? What that's saying is, if this actually was the truth, is it mathematically possible to get this result? Yes, but how likely? Well, when I look up the probability that z is less than negative 2.60, my calculation, where's your table?
Which one?
Got it, z. Oh, you have it colored out?
Yeah, it's right there.
No, you see table.
Oh.
This.
Oh, now I'm looking at the detail.
Yeah. All right, guys.
Okay.
So when I look that up, -2.60. The probability of being smaller than that is 0.0047. Now, 0.0047. 0.0047. Bye-bye. So if I was going to reject it at 1%, the probability of this outcome is less than 0.5%. So in English, if this were true, I can get results this extreme that often. That's not very often. That's
So I'm
really
going to reject
small.
it.
Absolutely. It's what a lot of stats courses do. A lot of stats courses.
So what goes right there?
Oh, no. This is correct.
Okay.
This is the p-value. So this is like Salvador said. He said this is a way to kind of confirm what you just said.
Look up z-score.
So the p-value, in high level statistics, people only use the p-value.
Okay.
They'll say, if my rejection, this is the 0-1 level of significance. If my p-value is smaller than 0.01, then I reject it because I'm saying it's really unusual.
Really? Okay.
If my p-value was great than 0.01, then I didn't reject it.
That's really
That's
awesome.
way less.
I got
than
it.
0.01.
I got it.
What's happening, man?
Thank you.
Long time no see.
How are you?
What are you, yourself?
Yeah, we're killing. We're killing. We just finished stats. Are you tutoring? Are you tutoring?
I am tutoring.
You are tutoring.
I'm tutoring the entire calc series, pre-calc, and linear.
Wow. How did you manage to get all of those?
Mostly for you.
I thought you'd only asked me about like a couple of the classes.
Calc 2, calc 3, and linear. I took a calc 1 assessment, and they embedded me in pre-calc.
That's awesome. That is really cool.
I've actually been trying to, cross paths with you because
Well, Tuesday and Thursday, I have an absurd break because I have such an early class. And I don't teach till over 2 hours from now.
Wednesday we're just opposite schedules.
Yeah, I've run into Tom a couple of times this semester, and he told me the same thing. That, in fact, he said he went on my office, and my office had moved, and I laughed. I go, "You stuck on the 3rd floor, didn't you?" He went, "Oh yes." But I do that, every few weeks. God, he was certain that I had moved offices because I wasn't there on the 3rd floor, but I never was on the 3rd floor. No, it's been an interesting semester.
And I must admit, I am